faster LLM pipelines with async batch calls. By the end, you will be able to run many LLM requests concurrently, keep each reply tied to its prompt, and measure batch latency so you can tune throughput. You will see a minimal working pattern that echoes inputs, ranks results, and preserves identity for safe post-processing. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Async batch calls cut latency and raise throughput. You reduce idle time by overlapping waiting for one model with work for others. The trade-off is memory and burst pressure because more parallel calls use more sockets and more model tokens. At small scale, you might have end-to-end time. At large scale, you must cap concurrency to avoid timeouts or rate limits. Think of async batch calls as sending a group of letters at once and checking replies as they come back. It shines when many independent prompts need similar processing. It limits wasteful waiting, but it can complicate ordering and error handling. We will keep a small, controlled example so you can apply the same pattern to bigger systems. We will build a tiny demo that sends prompts, gets uppercase echoes, ranks responses, maps replies back to prompts, and reports estimated batch latency. Now we run one simple asynchronous call. This snippet makes one asynchronous call that returns an uppercase echo. This snippet shows the minimal async pattern and demonstrates a single request round trip. It is intentionally simple so you can hear how an async call looks in the flow. You will see how awaiting a single result frees a worker to do other tasks in a real system. If you increase the simulated processing time in this snippet, the apparent latency grows linearly. If you instead repeat the call many times without parallelism, total time grows linearly with each call. This single call is our baseline for later batch comparisons. Next, we launch a small batch of parallel calls. This snippet launches a small batch of asynchronous calls in parallel. This example shows how to fire many requests at once and then wait for all replies together. You will learn the pattern of grouping prompts, starting all calls, and then gathering results. If you increase batch size, you improve throughput until you hit external limits like rate limits or connection caps. If you lower batch size, you reduce memory and burst risk, but increase per-item latency. This snippet makes the trade-off visible by comparing total elapsed time against the single call baseline we just saw. Now we filter and pick the best responses. This snippet ranks batched results and selects the top two by length. Here, ranking is simple and deterministic, using response length as a stand-in for quality. The snippet shows how to sort a collection of replies while preserving the batch's parallel nature. If you change the ranking metric to something like token probability or a separate relevance model, you affect compute cost and the stability of the selection. Picking top two illustrates batching plus post-processing. You batch for speed and then run a small, synchronous ranking step to select the best outputs for downstream use. Next, we keep prompts and replies aligned for safe processing. This snippet preserves input identity by mapping each prompt to its reply. It demonstrates building a stable association so you can trace which user input produced which output. The pattern is to attach an identifier to each request before dispatch and then rebuild pairs after gathering replies. If you alter identifier strategy to use sequence numbers, you keep order cheap and reliable. If you instead rely on implicit ordering, you risk chaos when calls finish out of order. This mapping is essential when you want to log, audit, or apply further per-prompt logic after the parallel phase. Finally, we estimate how long a batch takes to finish. This snippet estimates batch latency using the longest simulated call. It shows how to derive a conservative latency estimate from the slowest member of the batch, which is often the real gating factor for synchronous downstream steps. The snippet simulates call durations and reports the maximum as the batch latency, and it also computes mean and median for context. If you increase per call variability, the maximum tends to dominate and makes peak latency worse. If you reduce variability or cap concurrency, the estimated batch latency becomes tighter and more predictable. Recap: Async batch calls overlap waiting to raise throughput. They shine for many independent prompts, and they require careful limits on concurrency. Use them when latency and throughput matter, and avoid them when stateful sequential interaction is required. One caveat is resource pressure. More parallelism needs more connections and memory. Next step, measure this pattern on a larger corpus and add timing and accuracy checks. Then tune the batch size and the concurrency cap to find the sweet spot for your model and network. If practical AI engineering helps you, subscribe and watch the AI engineering videos.